Okay. Last step is I just want to show some very simple trie code here based off of a dictionary of 26 letters in the English alphabet. So the alphabet size is going to be 26. The way that we convert a character to an index, so we can do direct index into the children, is just by exploiting the fact that the ASCII code increases from A to the letter Z as increasing integers. So we just can subtract the two character codes. And I call that chart index. So we always have to have that associative array that maps a character to an index value so we can look it up immediately in the child. That's the key. Then the trie node is just incredibly simple. It's just a pointer to all of the children and their alphabet sized children. So 4 in the example that I tried to hand draw, 26 in this example. And they can stay null if you don't have any word that requires them. Otherwise, you have to malloc them. And then we just have an end of word marker, which is a 0 or 1. Okay, so it's ridiculously simple. It's just expensive memory-wise because every single character is going to get all of this node and all of its children with it. So we need to be able to allocate a node when we get to a point in the tree that a child is null and we need to add a character. So allocating a node is just mallocing a trie node, setting end of word equal to false, and then setting all of the children equal to null. Okay, that's just a regular malloc of a node like we do with all our trees. We want to insert, we have to get the length of the key that we want to insert, and then we have to start descending into the tree and seeing if those characters exist. So the first thing we have to do is find the index associated with that particular character. So the key at that level is just the character associated, with the whatever character in the key. And then if it doesn't have children, then you're going to have to add children. Otherwise, you descend down the tree. And if you do, when you're finished, you have to do the end of word marker bit. Okay, so that'll add just like the way I showed you. And then when you search, you do the same thing. You get the length of the key, and then you start descending into the tree. And if you don't find something, you return false. Okay, if you hit null children before the end of the word, it's false. Otherwise, you keep going, and finally, as long as you have found it and you have an end of word marker, then it's true. And that's it. That's exactly what I showed you in very simple C code, very elegant. And there's a simple little driver that shows the process of inserting some words and then searching for them and showing that they're there. Okay, so it's if you're willing to spend the memory, and if you have a lot of words that have common prefixes, and if you want to do something like autocomplete, it's a really nice data structure. What I want to show you next is a way to be a little bit more intelligent about storage. So we can often take two different data structures and combine the best of each and come up with something that has, slightly less wasteful memory-wise, but still retains the really nice thing about these, which are that we have constant string length, we have constant time search. Okay, so we'll look at that next.